Welcome back. So now let's go into the details of Quantita text analysis. So in the previous session, if you remember, we split our text data into train and test set, and we explained why we need to split our data for machine learning, and we have also labeled our text data, this bibliometric bib text data. We read our bib text data in R, and then split the data, assign labels COVID and SARS because we are labeling here. So if you remember, but for this session, I will just proceed directly into Quantida. So the first thing you need to do all this, the tokenization and all these word cloud or corpus designs, I think we will have to first load the package Quantida, which is actually my favorite package. So let me once you load the package, maybe let's see what are the names of our test data or train data, because we just want to see the variable names we have. So our variables, we have 7 variables. So we have the year, the title. We are mainly interested in abstract, and then the last one is the outcome variable. So we are actually mainly interested in these 2 variables. So we will use this for text data, and we will use bibtext key as a doc identifier. So the Quantida tells you to first identify the label variable. So the label variable, let me just call it train data, and train data, because this is the 6th variable, actually the 7th. So this is my 7th variable. That's my 7th variable. So the train data, that will be my 7th variable, and then for the test, I will just call it test data. Let me just call this one test, and again I have to change this into test. Then it will be my label variables. These are my labels. So let me just labels, or maybe dependent variable or outcome variables or something. But usually in the machine learning language, they're called label variables. But which in epidemiology you may usually call it outcome or dependent variable or something like that. The second thing is we need to create corpus, our text corpus. That's what we need to create. So let me call this train corpus. So for the train corpus, I use the corpus function, and this corpus function actually helps me to create a corpus object from our available sources. So you need a character vector, and then you create a data frame or a table based on the doc ID identifiers. Let me just take a corpus, and let me take train, because I have the train data, if you remember from my previous tutorial. So this is my train data, and the data that I am going to create a corpus from is the abstract. I just need the corpus should be made from the abstract. Corpus is actually corpus means structured text data that you would like to do pre-processing. So you create a corpus which is a structured text data. Then to create that structured text data, you use this corpus function from Quantita. The next thing you use is doc vars. These are document label variables associated with each text. So you can simply take a few variables, and let's take names of actually we can also probably see bibtext key, that means the 6 and the 7th. Let's try with that, because we want to use the 6th variable as a doc identifier, and maybe we can try that. If it doesn't work, then we will just work with our label variable. But this is not actually a label variable, but we are if we use 6 and 7, then it will not be a label variable. But let's just use the 6 and the 7 if you would like to include other variables. And then once we have that, what we do is we can create names. So we can actually the first thing we need to do is data frame. So we say data frame because we want to put these two variables in a data frame. So data frame, and then let me call it abstract label. We call it just like that, and abstract label. Maybe I need to push this a little bit here, and let me get this back. And data frame abstract label, and then I create names of train data. So these are the train data. The names are actually I need to take bib text key and the outcome variable, which is this include. So names, then train data. Then I can simply close this bracket. How many brackets do I have? So I don't need this one here. So let me just bring this up and put this down so that it can be more, can look more readable, like this. Yeah. So let me do this, and yeah, so that it works. So we have a train corpus. So we have the let me just pull it out and see train corpus. Yeah, here is our train corpus. So it's not a data frame, but it's a corpus object. Just like that, let me create again test corpus. So what I'm gonna do is I will change this to test corpus, and then I can simply change this to test data frame. And the last thing what I want to do is I can change this into test data. Then I will have the test corpus. Otherwise, the rest of the code will remain the same. So I can simply run this again. Actually, it will get it will be more readable if I put it like this. Now I can run this. Maybe I made a mistake. So test doc vars abstract label names. Okay, maybe error in check names false. Differing number of rows. Test corpus. Test data. Let me run this again. Maybe I didn't read it. And then let me read this again. Something is wrong. So test abstract label names test data. So test data is 261 observations. And what is the test variable? The test is also 261 observations and 7 variables, but test data is 261 observations and 2 variables. This is I mean, this is actually one of the problems that I noticed in Quanteda. I mean, it will work if I remove this. I was just interested to use bib text key as doc ID, but since it's I didn't change anything, so test abstract doc vars data frame abstract label names test data. So let me just copy this in case I made an error. Okay, so that doesn't seem to work, so let me just change this and just continue with my label variable. But with that, it should work. Usually work with that. Sometimes if you add more variables, in this case, it doesn't work. Now it works. You see, it's if when I add more variables, I think this is one of the problems that I noticed in Quanteda. But sometimes it works well adding more variables here, but otherwise you can simply add label data and then we can see. So let me now see the doc ID. That's the doc ID that I need. Is I just need to identify the identifier. I just need to find the identifier of the code actually. So let me just do something. Corpus names. maybe let me do this like doc ID, because I want to identify doc ID equals so then use paste function and train, that's label, my label variable. So let me use this doc ID, and once after that I use doc names and train corpus, actually train corpus, and then let me give it doc ID. Actually, I can simply use this one for this one, beep text, because it's a label identifier that I want to use. It's a yeah, instead of the decision variable, I want to use the beep text key. The beep text key is actually the right beep. Yeah, so let me show you beep text key, how beep text key looks like actually. So if you see the beep text key, let me scroll this down here, and these are how the beep text keys are written. So no, this one here. So this will be something, I mean, if you are working on a systematic review or something, so these are how the paper identifiers, like Pfister 2000, this is the first author, the last name of the first author, and the year the paper is published. So that's called, so we will use that bibtext key as doc identifier instead of the title, instead of the title or the author name or something, we'll just use bibtext key, and this bibtext key is unique, so it's unique. So we will use it as doc ID. Paste, train, bibtext key. Then once we do that, we can print train corpus. Actually, we can print train corpus. So let me just, I mean, if you print now train corpus, you will not have identifiers. So this is like text 1, text 4, text 5. This is how it's written. So instead, we will use our bibtext key in front of this. So when we print that, the bibtext key will be the text, the corpus identifier. So let me run this, and you will see how the corpus looks like. Yeah, now you see the bibtext key is used as the document identifier. So just like that, we can also do for test data. Let me call this again for test data. Let me just use this as test. Then test, and you need to be very careful sometimes. You know, when you copy and paste things, you may make a mistake. So then we call this doc ID test, and then once we have that, we take our train test corpus. So as I said, if I print this, test corpus will not have any identifier, so it will be like text 1, text 2, text 6, and it goes until 255, because we have 261, 6 of them are written here, and then 255 more are left. So for that, we need to assign the bibtext key as our text data identifier, and let me run all of this, and you will see the difference. So now you see this bibtext key, or the last name of the first author, and the year the journal is published. And sometimes, you know, when there are many similar last names, bibtext key is clever. It adds some identifiers, like to make it unique. So it does like 0.1, 0.2, 0.3 or something whenever there are, because it needs to be, this number is quite unique. Otherwise, let's say there are many similar last names, and then they have published in the same topic, in the same kind of, you know, theme, in similar years, so the bibtext key will be the same. But bib2df is clever, so it adds additional identifiers, so the bibtext key will be unique. Yeah. So now we have our corpus. So we have our corpus data. So once we have our corpus, the next thing we need to do is into the detail of the text processing. So when you do pre-processing, text pre-processing, so we have our data ready. Now we need to start with tokenization. So for tokenization, what you need is you can, if you know scientific articles, they are written like, abstract. Abstract is written, scientific articles. So abstract, if you have abstract, it's written as, at least in the structured abstract, you have introduction, maybe backgrounds in some cases. Some people write introduction and others write background. And then you have objectives, let's say objectives and methods. In structured abstracts, you will have results, and at least in most of the structured abstracts, you will have conclusions. These are the main things that you have. So as I said in the previous session, if you remember, if there is a term that appears in nearly 99 or maybe 95% or 90% or maybe 100% of the document, then that term is actually not relevant for your text classification. So you might be interested in removing it from your text data when you during tokenization. At the same time, if you have a very rare term, let's say it appears in only one of the hundreds of documents that you have, then that term is not really relevant, because if you remember, last time we were talking about TF-IDF metrics. So here is a formula what we have for the text data. We have this. First, we need to do term frequency. The term frequency is calculated as number of times term T appears in a document, divided by the total number of terms in the document. And then the inverse document frequency is the total number of documents divided by number of documents with term T in T. So that means if a term appears in all documents, then this number will be if the number is, let's say, I think it's better to give you the practical example here. So let's say, this is one abstract. It's actually unstructured abstract, because you don't see the introduction, methods, and discussion and the like subtitles. So in this abstract is written with 232 words. So COVID-19 appears how many times? 9 times. So to calculate term frequency, so you have 9 divided by 232. So if the term is like it's mentioned I don't know, many times in a document, then this number will be big. So if this number will be big, so that means this number, if the term is rare, so this number will be very low, and then this number will be low. But if the term is very common, mentioned many times, then this number will be high. This value will be bigger. But the problem with that, if it's really common, then you lose in the inverse document frequency one. So if that term is very rare, that means, very common, that means it's mentioned in many of the documents, then this number will be very big. In this part of the below, the denominator will be high, then this number will be quite low. That means if the term is abundant, then the term frequency inverse document frequency will be small. At the same time, if the term is rare, again the term frequency inverse document frequency will be tiny. So that means if you're really into improving your machine learning model by by those kind of techniques, then you may consider removing those like trimming those terms from the upper and lower extreme. Yeah. So first thing, so what you need to do is, as I said, you can remove these terms from your text analysis. So we can create a list of custom stop words. As I said, remember last time we were using stop words in tidy text package. So if you remember, we were explaining what are stop words. Stop words are terms that don't really change the content, or the don't really change the semantic, the semantic principle of the abstract. So if the abstract is talking about COVID, then if you have like words like is, or a, of, which is really quite the most common word in English language, and all these terms, they are really irrelevant words, so you need to remove them. Otherwise, they will just simply make your text data large, and you will pay in high dimensionality, in the curse of dimensionality. So then, so these are the stop words. So I will create another custom stop words, and these custom stop words are like this: introduction, aims, objectives, and the like. So let me just put it here, and maybe let me make it more readable. So I have a custom list of stop words. So I don't want background and introduction and aims, objectives, materials, methods, results. Maybe materials I can keep it. Sometimes people write it as materials and methods, but sometimes materials may represent different a different concept in abstract. So let me just remove methods, results, conclusion, and I'm using this textless because my abstracts may contain these alphanumeric characters, like alpha, beta, and all those signs, which my R software was not able to read them. And also in BibTeX actually can read them, but R converts these terms into something like textless. So I'm simply removing all those terms from my analysis. So this is how you create a custom stop words. You just list the terms that you would like to remove from your analysis, and then you can combine this with actually stop words. Now, the second thing is actually you can create your tokens. Let me create my tokens, my train tokens. Train tokens. The first thing is I need to do is let me build my train tokens. Tokens are actually, if you remember in our previous tutorial, it's about unigrams and bigrams that you want to do. So for that, Quantida gives you this function called tokens, and then you call your actually we can see how tokens function is actually, what are the arguments. So X is a corpus, and what you want is a word, let's say like a bigram or unigram or something. You can have a look at the detail of this package. I'll just proceed with a token analysis. So then I will just call my train corpus, and when you tokenize, so the first thing you need is you remove punctuation. You remove the punctuations, all these full stop, question marks. You don't need them in your analysis, and all symbols, they will also remove. And also you can remove numbers, and you can remove relevant and stop words, and also I can remove my custom stop words, the words that I created just above. So what I need is train corpus, and then I remove my punctuation. So that's what I need. I call this true. I want to remove my the punctuations, and then let me remove numbers. So it's simple. Quantida is very self-explanatory, so it gives you remove numbers, remove punctuations, and the like. So it's then you can run that. Let me run this in one line, and in the next line, let me again call it train tokens. But in this case, I would like to remove my custom stop words and the stop words actually. So let me use token select. Actually, that's what I want to use in the next, and then I call my stop words and custom stop words, and let me just put this down here so it can be more readable. Yeah, so the next thing, as I said, is you call token select, and then you call your train tokens, which is already here. And the pattern, I want to remove all stop words, and I can also actually I can combine stop words with what you can do is you can combine stop words with custom stop words, and then you can remove them. So in this case we are just step by step doing. So the first one is developing actually creating my tokens, and in this case here I'm creating my removing stop words. In the next one I will do removing custom stop words. Otherwise you can also combine both of them together and run your tokenization process. So now I want to remove my stop words. Then I will just simply do the same here. I'll just copy it, and instead in the pattern section I will simply call my custom stop words. I will just remove this because I already did it in the previous code. Now I can simply call my custom stop words here. Then it's the same remove, so I will remove them, these custom stop words, so they will not appear in my tokens, the list of the tokens that I want. So now I have removed all my custom stop words. Now the next thing that I want to do is I want to do my analysis. I do the same for the test data, for the test corpus that I created above. So I simply maybe I can copy them one by one. Maybe let me copy this and then change the data for text data. So I call this test tokens, and I call this test corpus because that's the data I have. And then again I can simply call my test tokens as I already defined it above, and then this one is also I need to call this test tokens. Let me again remove the custom stop words for the test data. Then once I have that, I can simply define my test tokens. So it's test tokens. Now I should be ready. I can simply run all of these lines, these three category of codes for the test data, and then tokenization process for the test data will be complete. So it will take a little bit of time until it's already complete. It's fast thanks to Quanteda. Now the next thing you need to do is you construct. So if you look at the train tokens, this is train tokens. They are like a large document, and which appear like this. So you need to convert them into some kind of format which you can easily do your text analysis. So for that, what we need is Quanteda provides us a nice function called constructing that helps you construct document feature matrix. I think in the text mining in the TM package is called document term matrix or term document matrix. So in this case, we create document feature matrix. So we create document feature matrix. It's what we will create. So Quanteda helps you to create this matrix easily. It's just one small. So let me call it train document feature matrix. And I simply use DFM function. I don't need anything else. I just need to define my train tokens. So train tokens, that's all. Simple. And I do the same for the test data. Test dfmat, and then DFM again. Test tokens. Now the document feature matrix will be done. and it's just simple 2 lines of code. No, DFM. It should be DFM, not DF1. So now I have the train DFM and test DFM functions. Now we can, because these are like data frames, it's kind of a large DFM object, but you can still be able to see the head and the tail, like normal data frames. So let's see the head of my train DFMat. Yeah, I can see the head of my train data frames. So if you see, I have about this 9,938 features and 98.9% sparsity. So that means there are a lot of zero values for some of the features. These are tokens actually. These are the tokens. So 2 words first explain your. So these are the tokens, but it's counted from each paper. So this is one paper, for example, and it's counted in every time the term appears. So it's counted again for the next one. For example, in this paper, determinants appear 3 times, and you continue counting for each. You continue counting terms for each abstract, and that's how it looks like. Then you can also look at the test DFM. You can simply look at the head of this. That's it, and that's how it looks like. So you have again 6,314 features. Again, it's highly sparse. Sometimes you may be interested in removing sparse terms, like sparsity. You can reduce it to 90%, 85% or something, and then that means you will trim. You will be able to trim these rare terms, like terms that are little value in your data. So you can cut them down, you can remove them. Okay. So okay, maybe we can stop it. I think it's more than 30 minutes of the video. Maybe I can simply continue to the next session in the next video. Yeah, as always, I would like to recommend liking or sharing the video to people who might be interested in it, or subscribing to the channel so that you can keep up on my next video. Until my next video, thank you very much for following up, and keep waiting for the next one. It's coming soon.